Hi, and welcome to the third video in a series about topology. In the previous video, we looked at the idea of a function, how to define it through the rule of assignment definition. We looked at ways to take composites of functions, that is, build new functions from existing ones, just the way we did sets in the first video. And as I mentioned towards the end very briefly, in this video we're going to take a look at something called a relation. And a relation is sort of a more general construction or a more general concept than a function. And we can in fact get right into the definition of it. So the definition of a relation given on a set A, it's a subset denoted by C of A times A, so a Cartesian product with itself. So C is a set and its elements consist of ordered pairs or products of pairs of elements that are both in the set A. This notation here means that if we have this point, let's say xy in C, where x and y are both elements in A, then this is equivalent to saying that x cy with respect to this, this relation C. So this is read x is in relation to y, sometimes through C. So we want to look at some different kinds of relations and find some important information to do with them, how they might be useful, some examples of them. So first of all, actually, let's note that you might be thinking that the idea of a relation here, as we defined it, is quite similar to the way that we defined the rule of assignment in the previous video. And it is similar, but one can think of a rule of assignment as a slightly more specific kind of relation. Like a relation is a more general form of a rule of assignment, because those rules of assignment had that additional criterion of being well-defined in a sense, but relations are more general and their construction is less strict, so to speak. The first kind of relation that we'll be looking at is, again, like a lot of the concepts we've been looking at, extremely important in many areas of math, and that is the equivalence relation. Equivalence relations, let's give the definition here. It is a type of relation C such that it follows some additional axioms, and these axioms are listed as follows. So it says that for any element x in the set A, where C is defined on, x is related to itself. And this is called the reflexive axiom because you see that this is reflexive with respect to the element. And this is the first axiom here. The second one is that if x is related to y, then y is related to x. So it's symmetric because one implies the other, and you can switch it around to have a valid point in an equivalence relation. The third one, which is referred to as the transitive or transitivity property, the transitive axiom, is that if x is related to y and y is related to z, then this implies that x is related to z. So it filters through y in a sense, like y is like a bridge between x and z, and it's enough to show that these are related. So relation sort of extends in a sense. Yeah, so these axioms, reflexive, symmetric, transitive, sometimes RST, alongside the property of being a relation, is enough to declare that C is an equivalence relation. Here is some notation that we might use where C is generally for relation. Sometimes you might see uppercase R. That's less codified or strict as the notation we're about to introduce, where if you have an equivalence relation, one can almost unambiguously define it with this tilde. So tilde can be used in place of these C's here, and you can define it as follows here. So x is related to x is written x tilde x, similar x tilde y implies y tilde x, and then transitivity is written x tilde y, y tilde z implies that x tilde z. So this is just more common notation to show equivalence. Now we look at an important construction, and we look at a certain kind of subset or a certain set that we can look at with respect to this equivalence relation. So that it defines this these kinds of sets on wherever the relation is defined. So given this equivalence relation tilde on a set A and an element x in A, we define something called the equivalence class of x in A, and sometimes the equivalence class of x with respect to tilde. This notation here, I don't think it's standard. I know that a lot of times the bracket is used, and more often than not, I've seen this tilde actually as the subscript here to show that it's with respect to a particular equivalence relation. Over here, I've just used the set A as the subscript because X is an element of A, and the equivalence relation in question is unambiguous as of now. So this equivalence class of an element, as it's defined, is the set of all elements Y in A such that Y is related to X. So it's all elements in a set that are related to this element in particular. And we note that this is something where we can say, given any element of a set, we can define its equivalence class that will be non-empty automatically under any equivalence relation. And we know this because of one of the definitions of an equivalence relation, that is the first one, where if X is an element in A and you have any equivalence relation tilde, so X is related to itself, that is, every equivalence class at least contains that element itself. So each equivalence class is non-empty, and given any element, you can ascribe a certain equivalence class to it that contains at least that. So they're non-empty. And we want to now look at how equivalence classes interact with one another. That is, like how their structure is regarded in a set, and how they might, do they overlap? Do they not overlap at all? As in, like, are they disjoint? And the important lemma here that we'll write and prove is that any two equivalence classes, and by induction or extension, we can say that any number of equivalence classes for any equivalence relation will be either disjoint or equal to one another. So let that sink in for a moment. Disjoint being their intersection is null or empty. They don't share anything. Either they don't share anything at all, or they share everything. That is, they agree on every element, and that is, they're the same set. So it's sort of two extremes, the way that these equivalence classes interact, either totally disjoint or equal. And we want to show this because it leads to another important construction, which we'll see in a moment, called a partition. So these equivalence classes, to show that they're either disjoint or equal, we can start by postulating, if we have these two equivalence classes defined with respect to elements X and X prime and A, let's say, that if we have these two sets that are disjoint, if we want to show that they're, let me rephrase this. We can say that these two are not disjoint and work towards a conclusion where we show that they are equal, and that is what we're going to do here. So if we suppose by construction that these two equivalence classes are not disjoint, that is, they're not equal to the null set, then we can find at least one element in their intersection. So Y, let's denote that element. Y is in this intersection here. And by the definition of intersection, where we think of it as like and, Y is in this set and Y is in this one. So we can break it apart into two separate statements that are equivalent. So we know that Y is in the equivalence class of X and the equivalence class of X prime, if it's in their intersection. So if now this element Y is in an equivalence class of this element X, similarly for X prime, by definition of an equivalence class, we can write Y is equivalent to X and Y is equivalent to X prime. So this is just by definition, and we want to show now something between X and X prime. If you don't already see it, which we'll just work through now, we want to show that X is in fact equivalent to X prime. We can do this through two axioms in succession. Symmetry first, for turning this Y is related to X into X is related to Y. So this over here and this, we can see now sort of lining them up, this and then this one. It filters or bridges through Y so that X is now equivalent to X prime. So by transitivity, we can conclude that X is equivalent to X prime. Okay, so we've shown this. And now we want to show these sets are equal to one another because that's our end goal. And to do this, we reiterate the important idea that we can show two-way containment. That is, if we want to show two sets are equal, let's say A and B, that we can show that A is a subset of B and B is a subset of A. And that's exactly what we'll do here, pointwise, by taking arbitrary elements. So let W be an arbitrary element in the equivalence class of X, and we can write this as Y is equivalent to X by definition. Now we know by transitivity, again, that W is equivalent to X prime. And it follows from this that W is in the equivalence class of X prime. So we showed that this is in this element W is in this, and that directly implies that it is in this. So hence, this set, this equivalence class of X is a subset of the equivalence class of X prime. And the second part of this proof, the final part, is directly analogous to this. We just switch around X and X prime now because there's no real, there's no generality lost there. So we've showed this one-way containment, and now we take just W prime now as another element, which we know is in the equivalence class of X prime, and we proceed just the same way. So we show that W prime is in the equivalence class of X, so this containment holds, and we have satisfied our conclusion. So this is all to prove that any two equivalence classes are either disjoint or equal. And this motivates another definition, another idea called the partition of a set. So subsets partitioning a set, which is motivated from equivalence classes, one can see. So we claim that equivalence classes partition A with respect to the following definition, where a partition of a set A is a collection of disjoint. First of all, their intersection is empty, non-empty, so they contain at least one element each, subsets of A, whose union is all of A, so they cover it in a sense. And we know this first part, disjoint non-empty subsets, because disjoint and non-empty were shown prior, and union is all of A is actually a direct corollary from equivalence classes, because we know that they're disjoint, so that's one end, and then union being all of A, every element has a corresponding equivalence class. So since every element gets sent to equivalence class, a unique one, then this union is all of A. So this is a true definition. This is a true statement here. Here's a little visual interpretation of how to think of equivalence classes, maybe. More generally, partitions. So we can take the set A and sort of break it down into these blocks of subsets like lowercase a through F, which is a partition of a set A in that these individual subsets are non-overlapping in any elements, but if you take their union, all of these together are going to give you this whole set, this overarching set A. Okay, so this is a good exercise to sort of write out in full, because it really deepens the connection between equivalence classes and partitions of a set. So given a partition, which we'll call D, the collection of subsets that satisfy these properties of a given set A, then you can define a unique equivalence relation on the set A. To do this, one might want to think about, well, given a partition set, that is, if you have the set sort of sectioned off like this, and you take pairs of elements in this here, how do we show, or how do we suppose that any two elements are equivalent? Like, how are we going to define that this equivalence here? So that's good to think about. Now let's look at another kind of relation, which is going to be extremely important later because it forms the notion of an order topology, as we will see. So this is called an order relation. And a relation C on a set A, as we've been defining in general, is an order relation if it satisfies the following axioms. And we list them here. So the first one is that if for all x and y in A, x is not equal to y, implies that either x is related to y or y is related to x. Something I should specify here is that this is actually exclusive or, so it's either or. One of these two must hold, and not both at the same time, and neither one at the same time. And the second one is that there exists no, that's this crossed out, there exists sign, element x in A, so that x is related to itself. And this is directly contradictory to the first axiom that we defined for an equivalence relation, that is reflexivity. So we see that something cannot be an order relation and an equivalence relation at the same time, just by virtue of this. In fact, the name for this is non-reflexivity, while the first one is called comparability, because it sort of dictates how to compare any two non-equal elements in an ordered set. And the third one simply is transitivity. So this actually is shared, and we have this definition here. So These are the three axioms for an order relation. And if this seems a bit abstract, let's change around the notation and see if it actually makes more sense now. The quintessential order relation is this less than here. So now rewriting, we can say x is not equal to y implies that either x is less than y or y is less than x. So this is the idea of an ordering. Non-reflexivity, this is an equivalent definition as one can check. X being less than y it implies that x is not equal to y. So these are mutually exclusive, being less than and being equal. And the third definition, third axiom is transitivity, so x is less than y, and y is less than x. Again, it sort of connects through this, and x is less than z. So this hopefully makes a bit more sense now with this notation, less than. We can call any set with, by the way, an order relation now an ordered set. We can just call it that. It's sometimes called a linearly ordered set or a totally ordered set. There are a few terms for it, but we'll just call it an ordered set for now. And here are some definitions now. So if x is a set, so now we're taking x to be the set with an order relation which we denote by less than, and if we take two elements a and b that are related in this way, that is a is less than b, then we can define this open interval, or just interval, this interval which is the set of all x that is, in a sense, between a and b with respect to this relation. So a is less than x is less than b, it's everything strictly between it. And if a, b is empty, that is, if there is no x such that a is less than x is less than b, then one can think of a and b as being adjacent to one another in a sense. They're directly, they're right next to one another. If there's nothing between them, there's nothing really separating them with respect to the order property of the overarching set. And we can say these two equivalent things, which is that either a is the immediate predecessor of b, or b is the immediate successor of a, and one implies the other. And this makes sense with immediate and nothing being in between them, sort of. Now, we're going to see how we can define something called an order type. So again, relations now which have to do with maybe different sets with their own corresponding order relations. And to do this, we take two sets A and B with order relations less than subscript A and less than subscript B to denote their respective sets. Then we define A and B to have the same order type. And this is if there exists a bijection, a map F from A to B that is both injective and surjective, or it's a one-to-one correspondence, that also satisfies this additional property, which is about the order. If A1 is less than A2 with respect to the order relation in A, then F of A1 is less than F of A2 with respect to the order relation in B. That is, one can think of this bijection F preserving the orders of A and B. So it's really a statement about the sets themselves and the way that they're structured, that this function, this bijection exists, that it preserves the orderings of each pair of elements like this. Here's a really interesting example to illustrate how two sets can have the same order type. And a somewhat unexpected one, I think, because you have this open interval in the real numbers, -1, 1, as a subset of R, and this turns out to have the same order type as the real numbers itself. So to do this, we need a bijection that is also order preserving. So we check this in sort of two stages, if you would like, and we have to find one first. You can check that this is a function that actually satisfies all of those properties. You can do this algebraically, or there's a really nice way of visually looking at it. And it's important to note now, in this case, we actually have these two less than relations the same because we're regarding -1, 1 as a subset, and it sort of inherits the order properties of the real numbers. So these two in general don't necessarily have to be the same order relation because, for example, A does not have to be a subset of B, but in this case they are, and that sort of simplifies things a little. So yeah, you can check that this function is bijection, that it's order preserving, all of that. But here's this nice diagram which actually plots this function. We're confining its domain to -1, 1, and we're seeing its its range here. So we can see it's surjective for sure, because every real number has the inverse image on this. That is like this sort of extends infinitely like this, asymptotically in both directions, and covers all real numbers. So we can see it's surjective like that. And we can see it's injective because we can sort of perform a horizontal line test now, where if you have a certain two certain distinct outputs, that they correspond to distinct inputs, or vice versa. So injectivity is this horizontal line test, if you want to do this graphically. And the order preserving nature is also something that follows from this. So not from the horizontal line test, sorry. So you can see the order preserving nature, hopefully, if you think about this for a little bit. But yeah, so this is just sort of an informal way of proving that this gives an order preserving bijection from this interval -1, 1 to all real numbers. Okay, so now we're going to show an interesting way of defining an order relation on a Cartesian product of ordered sets, actually. So we're going to start with this definition. Suppose A and B are sets with order relation less than A and less than B. So we can define this general order relation, which is just this general less than sign, no subscript, on the Cartesian product A times B. So we're defining some ordering of these ordered pairs. And we want to do this by defining, let's say, A1 being in A, A2 being in A, and say B1, B2 being in B. A1 times B1 is less than A2 times B2. If either A1 is less than A2 in A, that automatically qualifies this as this true, regardless of the relation between B1 and B2 in B. So this takes priority in a sense. Or if A1 is equal to A2, then we look at the second factor. So we look at the second coordinate, B1 and B2, in its corresponding set B. So we go element by element, with the leftmost ones having priority, and if they're equal, we go to the next one, so on and so forth. And this is kind of an interesting one, because you can think of it as like, if you're looking through a dictionary, how are you sorting words? You sort them first by their first letter, and you go letter by letter first, from words with the first letter A, so on and so forth, till first letter Z. And even within those sections, let's say all words with first letter A, you start sorting by second element, and if two words have the same second letter, then you keep going. So this is like a dictionary ordering, and that is in fact the formal way of referring to it. It's called the dictionary ordering on this Cartesian product of sets. And now, of course, there's nothing special about just having two sets. You can define this on a more general Cartesian product, and it might be good to write this out. I just sort of vaguely sketched it here, like having these corresponding order relations, these sets, and then you can really just go element by element as far as you like, just based on comparing these term by term or point by point. So this is the dictionary ordering on a Cartesian product of ordered sets. And we're going to look at now some very important definitions. You might have heard of the real numbers having a property called the least upper bound property. And this is actually a property that pertains to its order relations, or the ordering structure of the real numbers. So we want to look at some really important definitions that we're going to use frequently. Let A be an ordered set that is ordered by this less than relation, and let A naught be a subset of A. Then we say that this element B in A naught is the largest element of A naught, if x is less than or equal to b, that is, x is less than b with respect to less than, or x is equal to b for all x in A naught. So it's the largest element of A naught. There's nothing that is greater than it. So there is no element x such that b is less than x in A naught. And it's also contained in the set, importantly. And this makes sense, hopefully. And the second definition is that of being bounded above, or an upper bound. And this upper bound definition is that if for all x in A naught, x is less than or equal to b. And this might seem similar to largest element, but for one small subtlety, where in the largest element of A naught, this of A naught implies sort of that b is an element. So b, in fact, is in the set A naught. But bounded above supposes no such criterion, where a set can be bounded above by an element that is not necessarily in it. So it just has to have all its elements less than or equal to this upper bound. This is not to say that it can't contain an element that it's bounded above by, and in fact, if you have a largest element in the set A0, then this element B would also bound it above. But in general, an upper bound, as we define here, does not necessarily have to be in the set that it bounds above. And finally, we define this idea of a supremum. So let B, and this is the set of all upper bounds in A0. So this is read, the set of all elements B such that x is less than or equal to B for all x in A0. So it's the set of all elements in this set, the set A in general. It's the set of all upper bounds of the subset A0. Then if this minimum, if the set B has a minimal element or least element, then this minimum of B is called the supremum of A0. Sometimes it's called the least upper bound, because it is the least element that bounds a certain subset above. And there are actually corresponding or dual definitions for each of these, and they are, in order, smallest element, bounded below or lower bound, and instead of supremum, we have infimum. And it's a good exercise to see if you can sort of phrase these or reason these out in an analogous way to how we've defined these ones here, but they're all dual to one another. And now finally we can give this definition of the least upper bound property that you might have seen from analysis maybe. So an ordered set A has the least upper bound property, or the supremum property, if for all subsets A0 in A, if you're taking any subset, first of all, that it is not empty, and that it is bounded above. So these are the two prerequisites. If you have a subset that is non-empty and there exists an element that bounds it above in A, then there exists an element B0, which is maybe or maybe not equal to B. That is the supremum of, I should be writing A0 here. So there's an element B0 that is the supremum of the subset. In other words, an ordered set A has the least upper bound property if every non-empty subset that has an upper bound has a least upper bound. And the real numbers, in fact, have this property. There is, like we've defined sort of loosely for these past three definitions, a dual definition for least upper bound property, and that is greatest lower bound property, or infimum property. And once again, it is a good idea to see if you can phrase this in a way that's similar to how we defined it here. Okay, so wow, that was almost half an hour. So I hope you enjoyed this video. I hope it cleared up the idea of a relation, and I will see you in the next video where we're going to take a nice long look at the integers and real numbers and what really defines them. What are their properties and axioms based on what we've been looking at in the past 3 videos about sets, functions, and relations. So that's going to be a really fun video, and I hope to see you then. Thank you for watching.